Good morning, everyone, and welcome to our talk called Acoustic Virtual Reality as a Learning Framework for Built Environment Students. My name is Alessia Milo, and I am a postdoctoral researcher at the Building Acoustics Group at Eindhoven University of Technology. This work is part of a project called Acoustic Virtual Reality in Challenge-Based Learning, funded by Boost Innovation in Teaching from a university. We know that poor room acoustic design can impair cognitive processes, can make learning more difficult. Therefore, it is important to address acoustic design problems from early on in the design process. And one way to help this happen is to introduce acoustic design concepts such as reverberation time and intelligibility from early on to future architectural designers and engineers. For this project, we have a specific user group, which is made of built environment students, for example, first-year students who are attending a course called Baustudio at TUE, and they have to learn altogether construction systems, building physics, and architectural design. And we know that acoustics is just one of the many disciplines in building physics. So we would like at least to help them familiarize with the acoustic concepts at this stage. There are a number of papers documenting the use of VR technologies for construction, engineering, education, and training. Example uses are architectural visualization and design education, construction safety training, equipment and operational task training, and structural analysis education. One of the reasons why virtual reality systems are used in construction, engineering, education, and architectural design is because of their support towards head-and-hand tracking, so the user can interact with the scene. They allow room-scale exploration, and also in our case, it's very useful that you can listen to the scene while exploring the space. Given this background, our main research question was to find the potential and the limitation in implementing a realization of spaces that the students can edit in real time. So we first reviewed the available systems, for example, Virtual Acoustics by RTWH, Raven, and EverTeams, but we had some problems in finding something that could have already a real-time realization system for custom models and also would work with Windows and Unity in virtual reality. Our design process started from gathering the requirements for our use case. For example, the technologies available, their accessibility, the qualities of the users, and the sustainability of the project. We produced some prototypes that followed several design iterations based on feedback received from colleagues at the Building Acoustics Group and specialists, for example, acoustic consultant. We had in April 21 a first completed application with basic functionalities, and from April to October we extended some features based on the feedback collected and the time available. And we are now releasing the application for use in teaching with our students, although of course the latest developments are quite recent. And in the future we would like to improve the customization of the source code so that other researchers could use it for evaluation of rooms or for educational purposes. The Eindhoven Acoustic Virtual Reality educational tool will be explained by the following videos. I will now show you some functionalities for the Eindhoven Acoustic Virtual Reality application. Let's play some sound.
In 1895, Harvard University had just completed the Fog Art Museum, and the last conventional lecture room in the building had turned out, against expectations, to have very poor acoustics for speech. The university authorities approached the physics department for advice on what to do.
I have previously saved some different states for the room, so for example I saved the current one, and then I can switch between the different states.
And the department passed on the assignment to its youngest assistant professor, 28-year-old Maarten. Applied acoustics was not safe until.
Here you can find the materials assigned to the room, which are updated in real time.
And whether this scientific knowledge of the subject exists today.
And here you see the different absorption curves for the preset materials.
The problem was that excessive reverberation was obscuring the sound, and in order to correct this, we carried out a series of experiments with sound absorption so as to discover a mathematical formula by which you could predict the reverberation time of the room from its volume and from the sound absorption of the materials.
Here I have applied a custom material, which is one of these bottom ones, and I can edit these materials in real time. These were added in the original source code from Resonance Audio,
From which it was built. In doing so, he became the founder of modern acoustical engineering. He went on to design the acoustics of contemporary music, still considered one of the best forms of music in the world.
I will now show you some functionalities. I now want to show you the main functionalities of the application in VR.
The steady drip is worse than drenched rain.
This is the control panel, similar to what we have seen in 2D, with the room properties that we can still change. You can also listen to sound. And let's now try to load by using the file model. So for example, this is a small room. What I want to show you is that we can inspect the original materials, parquet on concrete, plastic, and we can change them. So if we bring some, you can see that the material is updated and the reverberation time is calculated. So also the average absorption coefficient curve is applied to the bounding box of the geometry, while the calculation is actually based on the real volume for the room. And I will explain with more detail this in the next slide. And now, here you have an overview of the EVR functional panels, which correspond to what you have just seen in the previous videos. We have a panel for the materials where you can select the materials, you can inspect the visual qualities of the material and their absorption coefficients. We have a panel to display the materials applied to the room. We have a panel to show the current reverberation time for 9 frequency bands from 31.5 Hz to 8000 Hz. We have a panel at the bottom to create observations and to load observations, which also includes setting a score for the current state, setting notes, and saving the observations. On the right, we have a panel to play sources, to stop sources, to change the gain for the source, minus and plus 3 dB, and select the source. And finally, we have a panel to increase or decrease the size of the room. We also added the possibility to import custom anechoic audio files in a dedicated folder. We added the possibility to import custom models, which were previously exported as GLTF from SketchUp, and we added the possibility to edit acoustic materials. Now I will explain with some detail the technical framework of the application. I would like to focus on the spatialization engine and explain how it works. We are using a modified version of the Resonance Audio library, which is based on applying a room effect to the listener. The listener is an ambisonics node, which has the possibility to appreciate the directionality of the source while moving in the room, and therefore the room effects are applied to the sources which are considered part of the same room. In our case, it is just one source. This room effect is made of two principal processing nodes, which are the reflection node and the reverb node. The reflection node uses what are called reflection coefficients, which are of course based on the absorption properties of the materials, and they are affecting the qualities of 6 delays, which are directional based on the main shoebox directions. These delays are therefore filtered and applied to the listener, and the reverb node is instead treated as a stereo node, which is a sort of noise on which it is applied some filtering, which takes into account the arrival of new reverberation times, and therefore, as you can you could listen earlier, it is fading into each other when you change the room conditions. This part is what was in the original code, but we modified this slightly. For example, we'd allow now Unity to get the absorption properties of the materials, and we also introduced 6 custom materials which can be edited around time. This was not possible. While in Unity we introduced also, besides the entire Edu tools functionalities, we also introduced the possibility to calculate average absorption coefficients that are then applied to the 6 filter delays, and we also introduced a recalculation procedure to retrieve the reverberation time values, which are then used by the spectral magnitude decay procedure. At runtime, we explored the room, we edit the shoebox, and we can import the model. The model is created in SketchUp. The user has to assign materials which have the same name of those in the application, and then export it as a GLTF. In terms of learning, we have 2 different comparison actions happening through what is allowed by the application. One is the comparison happening while the user is exploring the room and changing the materials, and the other is what can be done comparing 2 different previously saved states. We would like to continue evaluating the application in terms of usability. We did this with the previous version, but we would like to do this with the first-year students, which were our intended final users, and we would also like to know whether the application can help them learning about acoustics. In terms of limitations, we know that the calculation method, airing, is not suitable for every space. Of course, it is simplified and it works mainly for compact spaces, so for strain geometries, it should not be taken as the ground truth. And we know that the code is currently quite complex for someone else to work with, and we would like this to be reduced, maybe through some refactoring or redesign. Finally, the HMD integration is not universal, meaning that it only works with Oculus headsets right now, and we would like this to be more accessible. For the future, we would like to continue the development of the project for education and research, fostering open source collaboration. It would be beneficial to compare the results from this calculation with measurements or other simulation frameworks. For example, we would like to introduce the possibility to have audience absorption taken into account in the method, and the current library used to import the model, 3lib2, is not free, so it would be beneficial to replace it with an open source library to import GLTF at runtime. In conclusion, a technical solution, Edu, was developed to allow built environment students experience acoustics in VR. It will be introduced to the students in the coming months, thanks to our student assistant Jesper. Students can create models and experience different room acoustic conditions. It can be used with and without VR. That can be useful also when working from home. And also it allows sharing observation data. Moreover, we should remember that this is part of a bigger toolset And if you want more information, you can go to this webpage where we hope to be able to release the source code or access for those interested. So if you are interested right now, drop us an email and it would be great if you could collaborate further on this project. Thank you for listening.